Hi, welcome back to my channel. My name is Gina. In this video, we are going to talk about another type of force and its associated energy. If you haven't watched the videos that I covered type of forces and conservation of energy, I'll put the links up there. Force is a vector, so we are going to talk about the spring force's magnitude and direction. The magnitude comes from the Hooke's law. When an object is attached to a spring, its magnitude of force acting by the spring is k times the distance to the equilibrium point. The k is the spring constant, and it depends on the spring. Absolute of x is distance to the equilibrium point. Equilibrium point is when there's no forces acting on the spring. Then we set the natural point as the equilibrium point. And the direction of a spring force is always toward the equilibrium point. For example, here there are three sketches. The first one is when the spring is at rest. Then the position of the mass attached at the end of the spring, we'll call that the equilibrium point. In the second sketch, someone pulls the object, so the spring is stretched. Then what would be the direction of horizontal force acting on the mass? There is only one horizontal force here, and we just mentioned that the direction of spring force is toward the equilibrium. So here the spring force would be pointing to the left. In the third sketch, someone pressed the object so that the spring is now compressed, and direction of the spring force is now pointing to the right because it's pointing toward the equilibrium. And the magnitude of the spring force would be k times the distance from the object to the equilibrium point. The work done by spring, we denote that as W sub s, and it equals to half times the spring constant times the distance squared. Let's define the work done by spring as the potential energy due to spring. Then now we can rewrite the energy equation. In other video, we mentioned that if there is non-conservative force acting on the object, then the energy equation is initial energy plus the work done equals to the final energy. Now we are adding the potential energy due to spring into the energy equation. So now we can revise the equation to initial kinetic energy plus initial gravitational potential energy plus initial potential energy due to spring and plus work done by external forces, and this equals to final kinetic energy plus final gravitational potential energy and plus final potential energy due to the spring. Let's look at this example. A block of mass, 10 kilograms, lying on a horizontal plane, is attached to the end of a spring of spring constant K. The mass is given an initial displacement, 3 meters from the equilibrium, and an initial speed of 1 meter per second. The coefficient of kinetic friction between the mass and the surface is 0.1. Use energy methods to find its maximum speed and its maximum stretch from equilibrium. Let's start with a sketch. So there is a horizontal plane and a mass is attached to the end of the spring. The mass is 10 kilograms and it is 3 meters away from the equilibrium point. We know that the spring constant K is 0.2 and the coefficient of kinetic friction is 0.1. Let's start with part A. The maximum speed will occur when the object passes at its equilibrium point. Because when the block is at the right of the equilibrium point, the force will be pointing toward the equilibrium, which is toward the left. And when the mass passes through the equilibrium point, the force will now be pointing to the right, so the velocity will be decreasing. So the maximum speed will occur at the equilibrium point. So let's set the initial point as where the mass is released and the final point as the equilibrium point. So we have initial energy plus the work done equals to the final energy. Energy here includes the kinetic energy, and since the block is staying at the same level, so the gravitational potential energy is not important in this problem. And we also have the potential energy due to the spring plus the work done, which is force times the distance traveled times cosine theta. And this equals to final kinetic energy plus final potential energy due to the spring. Since the object is released, so the initial velocity is 0, so initial kinetic energy is 0. And we set the final point at the equilibrium point, so the distance to the equilibrium point is 0. So the final potential energy due to spring is also 0. Now we are left with 3 terms. Initial potential energy due to spring is half times the spring constant times the initial distance from the equilibrium point squared. And for the second term, we have force times distance traveled times cosine theta. Here the external force is the kinetic friction. We know that kinetic friction equals to the coefficient times the normal force. Here if we balance the forces in the y direction, normal force equals to gravity. So kinetic friction is coefficient times mg. And the friction would be pointing to the right, which is in opposite direction than the displacement. So theta is 180. And cosine of 180 is -1. So the second term is negative coefficient of kinetic friction times the gravity force, mg, times the distance traveled, d. And this equals to half times the mass times final speed squared. Now let's substitute some numbers. First term is half times the spring constant, 20, times the initial displacement squared, that is 3 squared, minus coefficient is 0.1, mass is 10, and g is the constant, 9.8, and the distance traveled is from the initial point to the equilibrium point, that is 3 meters. And this equals to half times the mass times final speed squared. Then we can isolate for the final speed, which approximately equals to 3.48 meter per second. Now let's look at part B. Let's find its maximum stretch from the equilibrium point. Now we are going to set the final point at where the object will reach to at the most left point. We are going to use the same equation. Initial kinetic energy plus initial spring potential energy plus the work done, and this equals to final kinetic energy plus final potential energy due to spring. Initially, the object is released, so velocity is 0. At the most left point, the velocity is also 0, so the final kinetic energy is also 0. So we are left with 3 terms. We have initial potential energy, half times k times initial distance squared, plus the work done, and is similar to the work done from part A. It's minus coefficient times mg. But now the distance traveled would be from the initial point to the most left point. And we know that from the initial point to the equilibrium point is 3 meters. And from the equilibrium point to the most left point, let's call it the final distance. So distance traveled would be xf plus 3. and this equals to the final potential energy due to the spring. That is half times k times final distance squared. We substitute some numbers. Half times spring constant 20 times 3 squared minus 0.1 times 10 times 9.8 times final distance plus 3. And this equals to half times 20 times final distance squared. Now we get a quadratic equation. We have 10 times xf squared plus 9.8 times xf and minus 60.6, and this equals to 0. Then we can solve for xf, which equals to negative 9.8 plus or minus square root of 9.8 squared plus 40 times 60.6 divided by 20. And we only want the positive answer. So the final distance from the equilibrium point is 2.02 meters. And that is the end of the video. If you like my videos, please like and subscribe, and I'll see you in the next video.